Hi friends, so we are into our course on risk conscious operations management for complex engineering system. And this is fifth week and very interesting topic, risk modeling and simulation. As we know, simulations have become integral part of most of the systems, be it aviation, be it nuclear, be it space, and this is basically to understand the various processes, their behavior, and as we always say, human is a integral part of any system. So even modeling human factor in the simulation. That way, this subject is going to go or going to tell us about what is the role of simulation and what are the additional advantages, and of course, like it happens with any other application, what are the limitation, and you have to be very careful because finally at the outset I will make a statement that a system's model is a model, whether it is a computerized model, thermal model, or electrical simulation, they are basically model. So there will be always a difference between model and the actual system. It is very difficult to create the actual system. In fact, this is an era of digital twin. So then this question becomes very important. What are the gap between actual system and the simulation that we are doing or digital twin that we are creating? So we are going to see more and more about it. My name is Professor Prabhakar V. Vardhe, and I am Chief Executive Officer of Engineering Risk Assessment and Management Center, ERMC call. And I am also a guest faculty at Luleå Technology University, Sweden, and senior professor, I have worked almost like 35 years at Bhabha Atomic Research Center, and there I retired as an associate director from reactor groups. So operation was my subject, I have dealt in operations all these years. I would say operation and maintenance, design project and all these things. So let us take up what is the role of simulation in complex engineering system. Okay. So I think there are 5 modules in this week, and the first module is we will discuss about the introduction and background, why we need simulation and what it means when we talk about the simulation, and then how simulation goes down to the level of we can do simulation at component level, we can do before that we can do at material level, that component level, then system level, and then finally at the plant level. So we will cover a wide range starting from component, system to the plant, and that is enabled by probabilistic risk assessment, because in probabilistic risk assessment you can create a risk model of the plant to get insight into the strength and weakness of the system. So we have introduction, then we have risk simulation for system, structures and component. When I say structure, it could mean a mega structure like a dam, or it could mean a component like a pump, and how it's a passive system or structures that are going to behave under different conditions. That is one thing. And then to model all these things, we require a background of probabilistic modeling. And then we have probabilistic risk assessment, which is a cornerstone of risk simulation. And then we have major elements of integrated risk simulation. Why we are calling integrated risk simulation? Because here simulation means using a plant simulator, which has got a role, like all deterministic characteristic will be represented by the plant, because plants are built from system and systems are built from component, and components are built from structural analysis or thermal hydraulic analysis. So that is the range that we have over here. Of course, all will not get equal importance. For us, it is the behavior at the plant level. What are the risk connotation or risk estimate that we have at the plant level, that will be our objective function. So let us go into the introduction. That is the week 5's first lecture. So background. Earlier time, when we wanted to understand the behavior of component, or even now also for certain conditions, we used to test the component and we used to have validation. But then the degree of freedom was limited, because if it is an expensive component, we can put limited number of component, maybe 1, 2 or maybe 10 or maybe 15, but then how much information will gather. But suppose if we create a physics of failure model of that component, and then it is basically computer based simulation, okay, and we will get a lot of information because we have all the degree of freedom to simulate different conditions. Of course, the model should permit consideration of those conditions. So in the scope, we should have a full scope, like it should at least be giving additional information what we used to get from testing and all that. Because simulation is you can perform a number of times. Role of simulation and modeling. Actually, when the plants are built, let's say when the plant is being built, it is in design stage. Now in design stage, very little information is there. If they are systems that are replicated, we do have some backup knowledge. But suppose a system is being created for the first time, and then what we need to have is, because every system is made up of a fundamental component, pipe, wall, electronics, if you talk, ICs, IGBTs, then resistors, capacitor, electrical component, inverters. So these components, they build the plant. I mean, we have some information about this component, but how they will behave in integrated manner at plant level, that is not known. So one is that information that is available to us, and we can simulate develop a computerized model based on that, and we can see how the plant will behave. Of course, it will not be 100% correct. 100% correct, definitely it will not be, because we know that it is a model of the plant. So suppose even if we reach 70%, our design team will get a very good insight into it. If I use this design option, how at plant level, even I can assess the risk also. So that is going to be the scenario. Now in here, we are talking about integrated approach. Integrated approach means it is not alone the simulation model on a computer of a plant, but it is going to be first a complete simulator, full scope simulator. It can be at different level of in terms of details. I will come to that, but we have a suppose simulator. That means I can simulate human actions there, because simulator basically they are meant for training, but there are a lot of scope to perform R&D also. So when we do R&D involving human, which otherwise is not possible till the plant has started, okay. So we have to have a lot of assumption, but here we can have, if we have a simulator, we can see the behavior. In fact, in design stage also a lot of information can be generated from a integrated assessment at plant level. Then probabilistic assessment. The role of PRA or safety assessment or probabilistic risk assessment, these two are the different names, but it means same. Either I call PSA or I call PRA. So we will be using, because our central is risk assessment, so we will call probabilistic risk assessment. So now once we have this model of the plant, we can develop many applications. We will talk about it in this lecture also, and then we can have a complete simulation environment. That means if I take out one component from a redundant system architecture, how it will affect at the system level, and then how it will affect will be at the plant level. That means what is the threat that this plant will pose for certain condition in some postulation of accident condition, And now with a PSA or PRA risk assessment, there are two application areas have developed, especially for regulatory domain, the risk informed application. That means if any decision is being taken, what is its impact on the overall risk at the system level or at plant level. At plant level it will be unavailability, and at system level it will be risk assessment. Okay. So it is better along with the traditional deterministic technique if we have the insight from PRA. So this is going to be very important in risk informed approach is basically very important in regulatory domain, and of course it can be used in plant operation design and all, because one additional input is available with us, that is variation of risk with certain configurational changes. And risk based. Often it is called risk informed, risk based. If we are building a plant and its application using the PRA model, which is complete in itself, and it is representing all the defense in depth provisions of traditional approach and redundancy, diversity to the extent possible, then it is called risk based approach. So and of course, even PRA model of the plant is also built from the plant configuration, which is basically from traditionally being developed through deterministic approach. So PRA captures all this redundancy, diversity along with its performance characteristic. Okay, probability of failure, failure frequency. So it goes one stage ahead and tries to give information on risk. And role of plant simulator and operator. Actually, simulators are basically designed for training, but they have huge potential for research and development. That what we are talking about. It's a application in R&D, especially for understanding the human behavior. Now here, as far as the first module is concerned, we are discussing some definitions. Then PRA, this will be the fourth lecture dedicated to it. Why simulation? We are going to answer this question. As I told you, it provides a lot of freedom when we want to study different configuration. In fact, for the trainees especially, it provides a big degree of freedom, because they can develop various sessions and see what is, so learning becomes much easier. Effectively, I would say training time should reduce in a plant where simulator is there, and compared to a plant which is not having a simulator. This is in principle it should be, but so far no study has been performed, but the experience says yes, it improves the training efficiency. So training and simulation. Training and R&D both goes on in simulator or simulation, or even if it is a risk monitor, I can perform so many simulation and see I can do optimization, I can solve optimization problem, I can develop some criteria for decision making and all. Advantages and limitation of simulation. The biggest limitation is it is a model of the plant. It is not the plant in itself. That means our validation, verification, and simulation has to back up what we are inferring from these models. Background is of course now we know that now we are in an era of advanced and fast computers and AI and all. So with that, simulation naturally becomes part of any development, especially engineering development. And if we talk about the development in terms of safety, yes, it is being actively used. Simulation is nothing but a computerized software. Like at the core of it, if I talk about the risk simulation, it is the Monte Carlo simulation. And now Monte Carlo simulation till 70s, 80s and 90s, our computers were slow, so it used to take a lot of time in computer. And this method used to be blamed that it is a very computer intensive, resource intensive and all that. But now we have very fast computers, so that limitation I understand has gone from there. And the objective is to assess the scenario, what is going to be in accident condition. Now these things are done by because a simulator facilitates all our plant postulated initiating accident or anticipated occurrences. Okay, so by running the session on anticipated occurrences, I come to know, because anticipated occurrences they happen at least once in a year, like power supply failure. It happens. So that way I come to know my model's characteristic, because it is happening in the real time also, in the control room scenario, if you see in plant also, and we are performing it. So basically we can validate validate the you can say our model, how far we are complete, in that sense. Okay, and then accident conditions also can be created. We cannot create accident condition in a real time plant, but here it can be created. And of course, it will be something more than what we have in design manual, which were the reference document where we used to read, and the thing was testing. So for safety system, we do testing. So all those testing scenario also can be generated on a simulator, and we can say where is the gap area, or is it better, or we are missing on something. So there are many ways to validate our simulation and all that. And of course, for risk, it is very important, because you know that it provides the complete deterministic side when we have a plant simulator. And most important thing is, in many accidents, or most of the accident, human factor has been found one of the contributory cause in the accident sequence. So human factor reduction, a lot of studies are going on at deterministic level, passive system, inherently safe system, they are being developed. But then for up to a scenario, what we have now is that we have to consider human factor, and operation per se is relatively human interaction intensive. So we should have a very good understanding of human factor. Simulation is a mathematical model, or we can say a logical model of the plant, and and benchmarking, validation and verification forms major. So at the end of anything, validation verification is the bottom line. Okay, since we are talking about the risk conscious operations management, in what sense we are using this term conscious? Conscious means, if I ask somebody, it means awareness level, focus, concentration. Okay, so these are the certain characteristics. So, what was there so far in the human reliability analysis? Cognition was playing the central role, but then the studies performed, it was found that first it is the consciousness which plays the fundamental role. What voltage bias is there for electrical system, consciousness is something for the cognition also. If our consciousness level is low, even in traditional sense, if consciousness levels are low, our grasp will be, take for example, some event has happened at night around 4 o'clock or 5 o'clock and all, and our biological clock, it has got its own model. So it is expected that efficiency during daytime will be much better than something happening at 5 o'clock or 6 o'clock. And if you look at the history, many accidents have happened during the night time. So is it that the consciousness was playing its role? No definitive answer is there. But consciousness is integral part of human existence. And in our risk conscious operation management, we are saying consciousness plays the role. It is a very significant factor. It tends to be more than the cognition, because cognition is driven by consciousness. These are one of the postulations of the CQB model that has been developed. So we come to a role. Consciousness is very important, and it should also become part of performance evaluation along with the cognitive factors, and that only model will be complete. Probably we all know that human factor, the human error probability, uncertainty factors are more compared to hardware component. I mean, it is not a sweeping statement, but we can see most of the times hardware components have, because the population is very high in hardware components, pump, motor, pipe. For pipe, of course, it is less, because there the reason is there are lesser failure, especially for, let's say, we talk about the primary heat transport system and all that. But then human factor, we need to have a lot of data, and that's how so that's why risk conscious operation management. Why? Because consciousness is integral part of operation, human consciousness. Now let us see, because since it is here I'll take a little pause and I'll say that I'll refer back to my earlier course on risk-based engineering, and there this probabilistic risk assessment also forms because for the continuity sake I have taken it here, this subject, but there internal risk, external risk, and it has been dealt in detail. So if somebody wants, they can refer my previous course on risk-based engineering in NPTEL itself, and then they can see the probabilistic risk assessment. Here I have taken those parts which are directly related to operations. The one which I have left, also they are related to operations only, because finally plant comes into existence and operation when design, other factors and all, aging and all there. But then here since it was I could devote only 1 week for this probabilistic risk assessment. So and that too is a part of risk simulation. So so let us see the definition. We have USNRC definition, which says the mathematical model of the plant for deriving the risk estimate. Comprehensive, they say comprehensive, because PRA is a very resource consuming comprehensive study. It runs into many volume, more than 5 to 6 volume, and then each volume is almost like 700, 500, 300 pages and all. So it's very time consuming, resource intensive. So it has to be called comprehensive, and it is basically to identify various scenarios and what are their frequency. So from IAEA glossary I have got this term, and then sorry, this is IAEA definition, first one, I am sorry. The first one is IAEA definition of the probabilistic risk assessment. This USNRC is like PRA is to estimate the risk by computing number of numbers to determine what can go wrong, how can go wrong. We have seen in our presentation earlier, and behind there is a plant, in the plant, and then finally a risk estimate. So likelihood and consequences we evaluate, and so now what to do? These two definitions are there, but I thought for risk conscious operation engineering, risk based engineering, I have to have a definition which can serve the purpose of risk conscious operation engineering. So I have put it here, a comprehensive, this word I took it from IAEA definition, and systematic and structured analytical approach to postulate the potential accident scenarios, because accidents have not happened. So we are doing postulation. Please note that whatever result we get in our analysis, they are postulation, they are result of postulation. Those events must have, like anticipated occurrence, they keep happening, and they also pose a small risk component. But but it doesn't mean that they are threat to operations or whatever. So but then accident rarely a plant, sometimes the plant run for 40, 50, 60 years, and 430 plants are operating, but major accidents have happened only in 3 plants. So what here, let us use this key term, postulation of accident, by considering numerical data on likelihood and consequences. This numerical data also, because my personal experience is the data collection, modeling, analysis, and finally converting them into reliability estimate takes maximum time of a PRA project, and I would say it is more than 50%, because at the bottom of this thing there is a consideration that good quality data can only represent the plant. If we take data, say for design stage, there are no plant specific data are available because it is under design stage. So there we have to have match the nearest estimate from the generic sources or similar plants data we can use, but we should be true to ourselves that in some way or other it should reflect the plant and its behavior. Okay, and then what are the outcomes of PRA? It provides the strength and weakness of the plant. So, weakness means there will not be a list actually. Sometimes if the experience is right, some 7-8 recommendation will come, and those things we have to implement. Some backup system or something like quality related issue or operation related issues, policy related issues. So those things will come, and we have to adapt to those and ensure that we are risk informed decision we are taking in implementing this recommendation. Okay. Now, in nutshell, what is simulation? Simulation is nothing but if I look at the any plant's this thing condition, there is a plant and its control room. So simulators, the replica simulator, they are exactly, they will look like control room only. That means we want to simulate the same condition as it is there in the real time plant as far as the control room conditions are concerned. And control room, 90% of 95% of the activities in the area of the plant, they are controlled or communicated through control room only. Okay, and control room is meant by one of the trained, one or two trained engineers. So all the decision flows from control room. So the control room becomes the central point, and that's how simulators have similar. But then, we have to rather create a simulator which exhibit control room condition, and it is nothing but a, now in plant we have data coming from field, wall, suppose hydraulic wall, it's on off, those data coming to control, status on data, various parameters they are coming to control room, and we take a decision, oh, plant's condition. So the human takes the decision if any deviation is there, and that's how plant is controlled from the control room. So that's how simulator is there. So here this data are trends, data trends and status, they are simulated from the backup computers, and for that we require a simulation platform, the tools which are there, and those tools they operate. And if you see, in fact, I will go to the extent of, even if a switch is there in the simulator room, it's a friction factor by rolling it will be the same as what we have in the control room, because finally a trainee has to go to control room and operate it. So he should be given the similar situation in the plant simulator the way it exists in the control. Even location of the parameter, everything is, this happens in a replica simulator, but sometimes we have non-replica simulator where space is considered limitation or something, or we want to do some new, like if I want to study video culture, that is visual display unit culture, most of the plants they have their mimic panels are they are having something like in lines, diagrams, static diagrams, in between some indication on off and all that, are trends there. But then if we do it on computer, one screen multitasking can be done, and all the important information can be brought. So similar, if you have to study the computerized digital control room, then simulator is the best platform where we can see the strength and weakness of video based or digital control room. Okay, that's how it is. And then now this is the era of AI and ML, and AI ML has already entered into operations and many tools and methods. Probably nuclear industry is very conservative, so as the experience grows, probably the AI ML will become even again integral part of the. At present, there is a digital systems, they are being incorporated, but with redundant safety provisions. Okay. So simulation in RCOM, what it does. Let's come to the specific. What it does in the. So we are trying here an integrated approach for simulation. Why we are calling it integrated approach? Because in plant control room there is a risk monitor. Risk monitor is nothing but PRA model of the plant. So in PRA we generate cut set. Cut set means combination of component that will result into undesired situation. So those things we take importance measure of the importance measure means again how the component is located and how its impact is going to be there on the overall safety of the plant or system. So this data, and of course location parameter and many other common cause failure and all those things are simulated. Human factor they are simulated. So risk monitors are there for this. Of course, in risk monitor we give the value, but those values are not generated from risk monitor. They are tested. How human factor, if it changes from high to low or low to high, how it will impact. But for studying the human factor, we have this plant simulator. So plant simulators are there basically as I said, it is meant for training only, but it can do wonders if we do R&D on that. And I think the experience of developing a human reliability model was very exciting because many sessions, in fact, in the plant simulator room, if you can monitor the alpha, beta, gamma, our brain's situation, wave, we will see that when we are in a stressless condition, there will be some waves that will be generated, and we are stressful condition or normal condition also, our wave pattern. So it can be taken or interpreted as level of cognition or consciousness, which is a very, very important insight that we get from control room. Of course, more and more studies have to be performed to underline the points that we are trying to talk about it. And then simulators can be good, but when we do at component level, let's say pump level, pump model is there in the simulator, but then that model may not agree with. So basically, if you ask me, creating a simulator based on physics of failure approach, so physics of failure or science based approach, then that is the ideal thing. But it is very difficult to have complex failure characteristic, complex the component level operations and all. So it was thought better to create the simulator based on performance characteristic that is generated. And of course, if you are lucky that you have performance characteristic, otherwise during design stage it is not available. So we can make a good simulator which will be more closely relating to the actual plant condition. Even if it is a neutronics, it will be for a nuclear plant. Monte Carlo simulation approach is applied for, and of course risk monitor, or whatever we call PRA model, all uncertainty characterization studies and all, they are done by Monte Carlo simulation. And then computer modeling is integral part of it. And of course now I would say digital twin is not much different than simulators, okay, because even the plant simulator is a digital model of the and it is much more complex than what we can talk about, and it is a digital twin. It qualifies now. The digital twin must be having some framework and all that, and some metrics for its qualification. But I think it represents the plant in a very effective way. So we discuss PRA and its role in simulation. And then we saw that it is now a lot of advancement is there in simulation approach, and if we can understand, validate its behavior, and that will determine how successful we are able to develop better simulator models. And in simulators, they play a very important role, or simulators or simulation. It plays a very key role in risk conscious operation management, because human factor has to be integrated, and PRA, best approach is PRA, and that is where, and simulator, where human factor finds better opportunity for its use. Even though the simulators are meant for training, but we have a very good potential, which I would say they are, in most of the simulators it is not that well utilized. That is R&D on plant human behavior and all that. Like stress level in different condition, people have kept, some plants have kept this thing, but how at R&D level a matured analysis and finding generated, that is yet to be seen. So this is our first module, that is introduction and background on risk simulation, and in next lecture we will again meet